Okay, example 9, the component method of vector addition. This will give us a chance to try out the technique that we just learned about in the last section 1.8. So if you haven't seen that video yet, please do check it out. So this example says a jogger runs 145 meters in a direction 20 degrees east of north, displacement vector A, and then 105 meters in a direction 35 degrees south of east, displacement vector B. Using components, determine the magnitude and direction of the resultant vector C for these two displacements. Right, so looking at this, the first step in approaching any problem is we want to draw a picture. And this is especially important when the directions start getting confusing like this. I'm already a bit confused, but we're going to try and detangle it together. So that's our first step, is draw. And since we know we're going to be working in terms of components, which we think of sort of X and Y pieces, I'm going to draw an X and Y axis as well. So Y is going up. We have X going to the right. All right, now my first vector says displacement vector A. It's 145 meters, so that tells us the length. Okay, what about this direction though? 20 degrees east of north. East of north. Okay, so since it's east of north, we have to start with north, which is straight up, right? Because remember that we have north, east, west, south. So we know we're starting out north and then we're going 20 degrees east. So we're tilting over by 20 degrees. So north would be in the Y direction, and I'm going to tilt over by 20 degrees. That is my vector A. Where this piece here, label it in black, is the angle that is 20 degrees. I'm sorry, the light is right on that. Okay, well, I'll share it bigger in a moment. And then it says we go 105 meters in a direction 35 degrees south of east. South of the eastward direction. So if from this point we imagine that we went east, we'd go purely horizontally, but it specifies instead that we are going south of east by 35 degrees. So my next vector is going to go downward actually. And this is my vector B. And then I can fill in that 35 degrees in up here. The only other pieces of information that I haven't already labeled that I know is I can add the lengths of these, right? That vector A says 145 meters and vector B is 105. All right, and so we want to find the resultant, so I'll fill that in too. And it says the magnitude and direction of vector C. Mag plus direction. All right, now that we've pulled all that information out of this problem, I'm going to stop the share. So that way you can see the board a little bit bigger. Again, sorry about the glare on it. Yeah, that helps slightly. So we can see the 20 degrees east of north and 35 degrees south of east. I know that's really confusing, but that's the thing. So how are we going to do this? Well, it says to use the component method, because if we were just using the graphical method, we could say, hey, look, our vectors are already aligned so that we can do vector addition. The tip of A is pointing to the tail of B, so we could draw in our vector C just based on visuals. Our vector C would be something like that. But we want to find both the magnitude of this and the direction of it. And that angle, we would have to draw very accurately in order to get an accurate angle for vector C here. I don't trust my drawing skills that much. I don't know about you. Plus it says to use the component method. So let's see if we can actually do that. So the way that we're going to think about this is breaking down vectors A and B into their X and Y components, their X and Y pieces. And we could start by drawing those visually, which I don't want to muddy this picture up too much, so I think I'm going to redraw each of the vectors individually. So I have my vector A, and this 20 degrees. And if I think of X and Y components of this, right, I could draw in A sub X, that's purely in the horizontal direction. I could also draw in A sub Y, that's purely in the vertical direction. Now the reason I'm doing this is that way it looks more similar to ways we've done it before. The other method you could use here is you could draw in A sub Y like so, and A sub X, and use the left side of the triangle, but your sine and cosine are going to switch, so that gets a little confusing. So I'd recommend instead doing this one. This will require a little bit of work to figure out the angle theta here, right? Because we don't know, we can do it in black. We don't know what this angle is. We know that the one up there is 20, and that can tell us what this is because together they have to add up to a right angle or 90 degrees. So this angle down here then would have to be 90 minus 20 degrees, or in other words, 70 degrees. Because the two of them have to add up to that right angle of 90 degrees. All right, so working with the 70 just to keep our equations consistent, we can solve for our X and Y components here, right? So the Y component will come from using the opposite here, which is sine. So sine of 70 degrees is equal to A sub Y divided by the hypotenuse A. Or in other words, A Y is equal to A times sine of 70 degrees. Similarly, we can get the X component with cosine. 70 degrees is equal to A sub X divided by A, or in other words, A sub X is equal to A times cosine of 70 degrees. And we could fill in that A value there, right? A is just 145. Meters. And so if we did that with 145 meters times sine of 70, then you should get 49.6. Oops, sorry, 136, excuse me. And it should be in meters for A sub Y and A sub X. That's the one that should be 49.6. All right, still in meters. I do want to show you though, because sometimes it's easier just to stick with the 20 degrees instead of doing this math to figure out the 70. So if we use the 20 to solve for, again, our AX and our AY, we would just switch our trig functions around is what the ultimate result is. So we would say sine of 20 is equal to AX divided by A. How do I want to write this? And similarly, AY is now cosine or adjacent to the 20 degrees. So cosine of 20 degrees is equal to AY divided by A. So this is where trigonometry gets a little bit confusing, but pretty cool as well. Sine of 70 is the same as cosine of 20, or cosine of 70 is the same as sine of 20. So whichever way makes more sense to you, please stick with it. Just be careful that you're making sure that you're referring to the proper sides, and that's where having a good picture is really helpful. Draw everything out explicitly. It will help you. All right, so let's continue on with vector b. We want to break b down into its components, and then we'll be able to add it all together to get our vector c. So let's see, I'm going to redraw my vector b here. So I'll first draw the horizontal, the eastward direction, and vector b is below the horizontal, going down. And we know that it's at that angle of 35 degrees. All right, getting a little lower here. It's a little angle down. Cool. So once again, I want to draw my x and y components. I'd encourage you to try that out if you haven't already. You can hit pause and draw them and then check your result. So what we should find is that there's a component of b that's pointing purely to the right. That is the x component, b sub x. And b is also pointing down, so we should have a down component. And that's a good way to check if you've drawn your x and y components properly, is they should match the overall direction of b. So since b is pointing to the right and down, my components should be to the right and down. Ha, that is comforting. And in this case, I drew them so that they are around the 35 degrees. That's very convenient. So we can once again approach this. I'll start with by since I started with ay. By is the side opposite to that angle, which is at that 90 degrees. So we can say that sine of 35 degrees is equal to by divided by b. Or in other words, I think it'll focus better if we could angle that down, that b sub y is equal to b times sine of 35 degrees, where b here is that 105 meters. So if you multiply that one out, you should get a number of 60.2 meters. All right, b sub x will follow the same procedure. It's going to just come from a cosine, just as a of x did. So it can come from b times cosine of that angle. 105 meters times cosine of 35 degrees. So if you calculate that out, you should get 86.0 meters. Great. Now there's one more wrinkle I haven't mentioned yet. We know that the x direction is pointing to the right, and we know in vector A, the x direction is pointing to the right as well. But if we look at the y direction, vector A has a y component going up, while by is going down. It's going in the opposite direction, or in the negative direction. That means we need to account for that. It's not enough to just plug in numbers and chug. We need to pay attention to the fact that by is actually going down, and so I'm going to add in a negative sign here. That it is in the negative direction, negative 60.2. Sorry, that point is pretty small. All right. So this has been a fair amount of work to get up to this point, but we are now almost there, right? We want to find the magnitude and direction of vector c. We can easily get, at the very least, the x and y components of c, and then from there we can get to the magnitude and direction. So I'll try to keep my color coding consistent here. We know that we can get the overall x and y components of c. I'll go up to my picture here for a moment first. So c sub x, c sub y, by just adding or subtracting the x and y components of A and B. So that's what we'll do down here. So Cx is equal to my Ax plus my Bx. Right? So we could fill in the numbers here that Ax is 49.6 meters. Plus Bx is 86 meters. And what we'd get when we added those together, actually I don't have it written out in my notes, but I can add them right here. It doesn't hurt to wait until the very end to do that. 135.6. So that is our C sub x. What about the y component? Well, it's going to be the same procedure, right, of adding the x plus the y. So let's make sure we're angled downward enough. C sub y is equal to my A sub y plus my B sub y. You could also argue that this is where we could put in the negative sign on the B sub y, but since we've already accounted for it, I'm just going to focus on keeping it positive. And to me, that makes more sense, that we're just adding these components, and by is a negative component because it's going down. So A sub y is the 136 meters plus B sub y is the negative 60.2 meters. So 136 minus 60.2. So 75.8. All right. So these are two good intermediate results. This would work if the problem asked us to solve for the components of the resultant vector C, but here the problem asked us to solve for the magnitude and the direction of vector C. That means the overall vector C, not its x and y components. So to get to those overall ones, we're going to need another board. Right. And actually, I'll work with this sideways, I think. So we can see our picture up there still. So we want to keep this picture in mind that vector C comes from Cx and Cy. That means if we want the magnitude, we can just use our relationship. It's a theorem. Remember it? Yes, the Pythagorean Theorem. So Pythagorean Theorem says that vector C squared is equal to Cx squared plus Cy squared. And I'm going to switch to black at this point so we don't have too much orange going on. In other words, C is equal to the square root of Cx squared plus Cy squared. And so vector C is equal to the square root of, let's peek what we got. Cx is 135.6 meters. I might have dropped that on the last one. I'm sorry about that. Plus Cy is 75.8, again, meters. And I'm so sorry I dropped that. Can't leave off our units. Goodness. You really got to speak up more when I'm missing my units. All right. So using the Pythagorean theorem here, we can combine those and we would get 155. With what units? Meters, exactly. And here I'm sticking with 3 significant figures. because that is what our data was. It specified 3 significant figures. All right, so this gives us the magnitude of the resultant vector. That's our first part of this. Cool, magnitude check. Now we just need the direction. For the direction, that's asking about this angle theta. And we usually want to find the angle theta based upon the y and x components, not the value we just got. So the way we can do that is by going to our tangent, or our inverse tangent, to be more precise. So this is an equation we've seen a few times at this point, that the angle theta is equal to inverse tangent of the opposite over the adjacent. So cy divided by cx. And now I can plug in actual numbers here. So inverse tangent of cy was the 75.8 meters. Make sure you get it right, so be careful that you copy that correctly. Didn't matter in the last one, the order, but it definitely does in taking the tangent. Divided by cx, which is 135.6 meters. And since those are both meters, the meters will cancel and we'll just have the inverse tangent of a ratio. So when you take that inverse tangent, you should in your calculator get 29.205, assuming you are in degrees mode. And you could just write that down because your calculator spat that out. But that's so many more digits than you're really confident of. Like, are you really confident that you know it to the 1,000th of a degree? Probably not. Probably you just know it to 1 degree, but in this case, because we have 3 sig figs, it'd be okay to write it to 3 significant figures. And we will get to talk more about significant figures in lab, the very first lab. So if you're new to them, then we'll get a chance to talk about those. So I would probably write this as 29.2 degrees is equal to theta. And those 2 pieces make up your final answer to the magnitude and direction of the resultant vector c when we add vectors a and b together. So there you've seen the component method. It is extensive. It's not something that's just a no-brainer. Your brain is definitely involved in physics, so yay for that. But it's very systematic. So as long as you follow a procedure, draw good pictures, then you can just work your way through it and you will get through it. If you have questions, please do ask. I am happy to help. And until next time, that wraps up chapter 1. So it's been a trip. Chapter 1 definitely packs it in. So congrats on making it this far.